Hi, welcome to today's lesson on electron excitation. The question of the day, Bohr said electrons can move around inside of an atom. If electrons are attracted to the nucleus, why would they ever move away from it? All right, we already know that electrons live in shells, clouds, orbitals, or energy levels in an atom. They're outside the nucleus. Now, based on the attraction between the nucleus and electrons, they're going to want to get close to the nucleus, but because electrons repel each other, they're going to find an individual sweet spot where they fit inside an atom, close to the nucleus, but away from other electrons. And in order to do this, we have assigned electrons an address inside of an atom, and we call that their quantum numbers. The first digit of their address or their quantum numbers is going to be the principal energy level that they're in. There are 7 principal energy levels. They correspond to the periods on the periodic table. So, for example, sodium, Na, is in the 3rd period, so its electrons fill 3 principal energy levels. So if we were talking about the single valence electron in sodium, its first quantum number would represent that it was in the 3rd energy level. Now, there are 4 sublevels that our electrons can be organized into, and they are labeled S, P, D, and F. And these things are going in 3 dimensions. They're all 3-dimensional. So it's not flat like the planetary model, like our solar system is a flat circle. And then we kind of just move in a circle this way. Electrons are moving not just forward and back, they're also moving side to side, and they're also moving up and down. So all of these orbitals, their sublevels are drawn in 3 dimensions. The sublevels can be broken even smaller into orbitals, and depending on the type of sublevel that an electron is in, it will have a few options for orbitals. So this would be the px, so it's the p sublevel, but the x orientation, the one that goes side to side. We have the p sublevel and the y orientation that goes forward and back. And then we have pz, which is the p orbital that goes up and down. Now we can have 2 electrons fit in each orbital. So we can have 2 electrons in px, 2 electrons in py, and 2 electrons in pz. This totals 6 p electrons. Your p electrons can be in periods or in energy levels 2 through 7. There will be more on this and how electrons specifically are organized in an upcoming video. I'm going to go into huge detail with all of this, but I just want to let you know that our electrons are very, very, very organized. So we can fit 2 electrons in each of these orbitals. And then finally, the last digit of the address, the last digit of the quantum number, is going to represent the spin. So we have 2 electrons in each orbital, but they are going to rotate around the nucleus in opposite directions. So one of them is going to be going clockwise and the other is counterclockwise. And this is kind of so that they can avoid each other and they're not like one following behind the other and they kind of spin together. They are going to go opposite each other. I don't know that I can do this. It's like patting your head and rubbing your stomach, but a little bit more intricate. Electrons are certainly better at it than me. So we would have 1 electron living in this lobe of the px, and then an electron over here. And then they will sometimes get near each other. They don't like each other. When they get near each other, they're going to zip away real quick. And up close of the S sublevel, there's only 1 S sublevel in each principal energy level. So in the periodic table, there's 1 S sublevel per period. And it is spherical and it holds 2 electrons. And I'm going to kind of give you a hack here. If you pull up a periodic table, and I know mine's really bright, so it's hard to see, the S sublevel is represented by the first skinny tower of the periodic table. So lithium, beryllium, sodium, magnesium, potassium, calcium, rubidium, strontium, all of their electrons, their valence electron is an S electron. And kind of a hack for this is that the S sublevel holds 2 electrons. That is why this tower is 2 elements wide. Then again, we have the P sublevel. The P sublevel can be found in periods 2 through 7. There are 3 p sublevels in total. I'm sorry, there's 3 p orbitals in total. Like I said, left to right, up and down, front and back, and then we have a combination of all of them together. Each orbital can hold 2 electrons, totaling 6. And again, if you look at the periodic table, this section over here is called the p block, and these elements have their valence electron in a p sublevel. And the way that you can remember that 6 electrons fit in a p sublevel is that this is the p block, and it's 6 elements wide. Then we have the d sublevel. The d sublevel is present in periods 3 through 7. And I'll get more into this later. There's something funny that happens in the D sublevel, but that's where your transition metals are. And they are the center block of the periodic table. There are 5 d orbitals holding a total of 10 electrons. So again, the center chunk is called the d block. And if you count, it's 10 elements wide. That's how you can remember that there's 10 d electrons. Now, this picture shows lots of variations of d sublevels. You have the one that's primarily going forward and back, and you have the one that's primarily going side to side, and then you have this loop-de-loop one with the ring in the middle. We haven't seen these with our own eyes. We just kind of predict what these sublevels look like based on how electrons behave. There are 7 f orbitals per level. So if we have each orbital holding 2 electrons and there's 7 of them, that's going to total 14 electrons. So on a nicely written periodic table, this block right here down at the bottom, that should be 14 elements wide. Sometimes it'll be 15 elements wide, but that is because the periodic table is kind of broken right here, where the yellow and the orange are in this main section of the periodic table. It's broken right there, and then those elements are slid down here just so it prints nicer. So I like periodic tables that have LA and AC up here, and then these guys down on the bottom should have just 14, but occasionally you'll see 15. So that's something else to remember, but that's how you can account for the F sublevel. So here is a summary of all of the sublevels and how many electrons they have. I know it's a lot and it sounds really crazy. I have always remembered this in order, and this is like the dumbest thing ever. Please don't make fun of me, but I remember it super penguins don't fly. I mean, penguins don't fly, but also super penguins don't fly. So these go up by 2s, starting with 1, 1, 3, 5, and 7. And then you just take the number of orbitals and multiply it by 2 in order to get the number of electrons. So that's the pattern here, the number of electrons that fit in each sublevel. And now this is where things get fun. We are going to account for how electrons can move inside of an atom without leaving that atom using an analogy that I call quantum estates. It's an apartment building. It's brand new. A bunch of electrons are going to move in, but the elevator hasn't been installed yet. We know that electrons live in clouds or energy levels of an atom, but because they're attracted to the nucleus but repel each other, there are some rules that kind of dictate where they're going to live inside of an atom. So we're going to imagine that quantum estates is a home to electrons in any element that you want. The catch is that the elevator was never installed, and the electrons must climb the stairs to get into their apartment each day. The building is empty, so the electrons can choose any room that they want to move into. And we are going to kind of direct them based on what we know about the atom and the rules that dictate electrons. So in the analogy, the building is going to represent any atom that you choose. The lobby, the ground floor of this building, is going to represent the nucleus. Each floor represents a principal energy level. Remember, those are the ones that correspond to the periods. Each room is going to represent an orbital, so S, P, D, or F, and then each bed in that room is going to represent a spin. We have the very first electron, and he gets to move into this building wherever he wants. And remember, the elevator is not installed, and the lobby is kind of the nucleus, so putting that information together, I'm sure you can guess where he wants to live. The very first electron is going to want to live in the 1s room. And this is because he's lazy and doesn't want to climb the stairs. But truthfully, it is because he is negative and the nucleus is positive and they're attracted to each other. Of course, he doesn't want to climb the stairs. He wants to be near that very attractive nucleus/lobby. And this in chemistry is defined as the Aufbau principle. Electrons are going to live in the lowest energy state that they can because they're attracted to the nucleus. So that means electrons are always going to try to be as close to the nucleus as they can get. So now it's time for the second electron to move in. And where do you think he's going to want to live? He is also going to choose the 1s orbital, or the 1s room, and this is because of the Aufbau principle. He wants to get as close to the nucleus as possible. And he's okay with this as long as he's close to the nucleus. He would rather be close to the nucleus than far away from another electron. Now, the room that is the next lowest energy is the 2s orbital, and that is the next room that is closest to the nucleus. So just like electrons 1 and 2 shared a room, electrons 3 and 4 are going to share a room, and they're going to choose the 2s room because that is the one that's closest to the nucleus. And then we come to the point of 2p. And the 2p rooms, there's 3 of them, 2px, 2py, and 2pz. And the question is, where are the electrons going to go? Electron number 5 is going to randomly select a 2p room. This is because 2px, 2py, and 2pz, remember up and down, left and right, and forward and back, all of those rooms have the equal amount of energy. They're all the same level in terms of the electron getting close to the nucleus or climbing up the stairs. So it's just totally random. It can go anywhere. And now electron 6 has an opportunity to move into some of those 2p rooms. One of them is occupied and 2 of them are empty. Where do you think this electron is going to go? The 6th electron is going to move into one of those leftover and empty 2p rooms. And this is because electrons are negative, remember. They do not want to double up and get close to each other if they don't have to. This is called Hund's rule. I also sometimes call it the bus seat rule. If you get on the bus, you're going to want a seat to yourself as opposed to sitting with somebody, especially if that person is like not your friend and they're a stranger. You're going to want a seat to yourself. So it's kind of that same way. Electrons repel each other. So if they have an opportunity to be far away from each other, but not get any further away from the nucleus, then they're going to take it. So this 6th electron is going to have his own room, at least for now. And this is because he's going to repel electron number 5. So for the rest of the atom, the electrons are going to fill following these 2 rules. They are going to try to get as close to the nucleus as possible, and they are only going to double up and share a room if they absolutely have to. They want to find empty orbitals that are of the same energy and find one of those empty orbitals, but when they don't have an empty orbital, they'll double up in an effort to be closer to the nucleus. Now we have a way to help us remember how electrons are going to fill quantum states, and it's called the diagonal rule. It kind of looks like this. The orbital filling is based on the amount of energy an orbital has, not specifically its level number. Our numbers kind of go a little bit out of order, and this is because when you have a lot of electrons in an atom, you have to account for a lot of repulsions. So it's kind of strange that right here, after 4s, you would go and fill 3d. So you start at the top, you fill this way, you do 1s, then 2s, 2p, 3s, 3p, 4s, and it's kind of strange that you skip over 3d and do 4s instead. And this part is because our orbitals are filling based on the amount of energy they have, not necessarily the level number. 4s is lower energy than 3d. For your purposes, you don't really need to know why. Truthfully, it's because our electrons repel each other a heck of a lot. And the bigger atoms get, the more repulsive forces we have to account for. And we don't necessarily know exactly what the repulsive forces will look like, how they work. We know that they repel, but we don't know by how much, and it's a lot. Also, our big atoms can take some of their interior electrons and rearrange them. And they do that so that they can kind of change the stability of some of these energy levels or where their electrons are. The culprits of rearranging are largely that center piece, like I was saying, the transition metals in this section here. Those are going to be the ones that are the biggest culprits of rearranging. So they are the ones that kind of mess up the diagonal rule. But it's okay, because with the diagonal rule, we have a kind of blanket statement for which ones are the lowest energy and therefore the most stable. But now it's time for a party. Here we go. A bunch of electrons have moved in. They've gotten comfortable living in their low energy homes, but now it's time for a party, and they're all going to head upstairs. Now, in order to get up the stairs, they're going to need some energy. So the electrons drink a Red Bull, they get some wings, and then they fly upstairs to higher energy levels. So in chemistry terms, we would describe this as the electrons absorbing energy in either the form of heat or electricity. Heat is going to be your flame test, where you literally add heat. You light your sample on fire or introduce it to heat. It doesn't usually set on fire. And that added energy is going to give the electron some energy to jump up to higher energy levels. You could do the same thing with a flow of electricity. That's how neon lights work. When they get this energy, they are able to overcome their attraction to the nucleus and jump up to higher energy levels. But the ground state and the nucleus will still always be calling them home, because that force of attraction will never be totally broken unless that electron totally leaves the atom. So they are going to be attracted. They're going to want to go back down to ground state. The electrons have to absorb a specific amount of energy to get from ground to excited. So the electrons, when the party is over, all of the energy has been spent, they have to go back home to their ground state. But in terms of chemistry, we would say that they are releasing their energy, and that typically is going to be released in the form of light. Again, the amount of energy that an electron absorbed to jump to higher energy levels is going to be emitted when it comes back down. So here we have a flame test. This might represent lithium. Lithium has a bright red magenta-ish flame. And that is what lithium looks like when you have its electrons excited. It'll jump up to higher energy levels, and then when it returns back down, it's going to emit light, and it's going to come out at a specific amount of energy, and that energy is going to be a particular color. We can also measure that using a spectroscope and get literal measurements for how much light is coming out of the sample. But the amount of energy that we put in is going to be equal to the amount of energy that comes out. So we have electromagnetic radiation, so heat or electricity. It is going to hit the electron, which is in ground state, and then bounce it to excited state. The excited state is temporary. It can only stay there for so long, and the nucleus is going to call back that electron due to its attraction. And because of that, the electron is forced to give out energy. It's going to expel, emit, spit out, release energy. And that electromagnetic radiation is going to come back out. And in this case, it's going to be colored light. So here's an example of some flame tests. Zinc has this nice pastel yellow. Potassium has a beautiful lavender purple. It's really hard to see on a Bunsen burner, though, because the lavender purple is pretty close to the blue flame. It works best when you have it, your lab is super, super dark. Strontium is very close to lithium. They're both like a reddish color. Lithium's a little bit more pinkish. Sodium and calcium are really alike. They're both an orangey color. Copper is my favorite with this greenish color. In my experience, copper is also a little bit more blue than this. Barium also has a lime green flame. So flame tests are good, but they're not definitive because it's really hard to distinguish the colors from one to the next. And also you can have some interference. For example, these are all done on little wires. So the sample is pretty good. When I do this lab as a chemistry teacher, I have the sample soaked into popsicle sticks, coffee stirrers, like these little tiny wooden sticks. And the wooden stick will also become excited. Wood burns with an orange flame, but that'll sometimes interfere with the colors of the flames. The light that comes out of these samples can be measured, and we measure them using a spectroscope. We're specifically going to measure the wavelength. So we have light exciting a sample, and then the sample is going to emit light, and we read it with a spectrometer or a spectroscope, and we would get something like this. We get this hydrogen emission spectrum. Hydrogen emits, I've never seen this fourth line, I've only ever seen the 3. Part of it is interference and how good your sample is. But hydrogen has these specific lines that come back, and this is how we can recognize that our sample is made of hydrogen. Every element is going to have a unique spectrum with measurable lines. So this is not something willy-nilly. This is a little bit fun. It's also pretty willy-nilly because a bunch of the flames look like they're the same color, but this emission spectrum measurement is unique. It is going to come back just for one element at a time, and this is how we learn some really cool stuff. We can take those spectral lines and use them to identify elements in a mixture. Sometimes that's cool, but what's even cooler is that we can learn about stars and galaxies and planets and things that are really, really far away by measuring the light that we're receiving from them. It's not something that you could do in your chemistry class because there's a lot of interference from our own sun and the light that comes from there. But if you were to study astronomy, and you were reading data that came back from some of our satellites and the cameras that we send out, then you can, interpret data from far away with very little interference. But this is how we learned that helium is on the sun. Helium was discovered using a spectroscope. It was pointed at the sun and hydrogen was identified. And then there was this other element that we didn't know what it was. And we named it helium, like Helios, the sun god. And a little while later, we found that same element on Earth. It's not super prevalent in the crust. It's more in the atmosphere. So it was kind of hard for us to find. But when we found it, we said, oh, that's helium. And we knew because we were able to match the spectral lines. So the sample from the sun had this, but for helium. And then we found it on Earth and we matched them up. Okay, I have 2 questions for you. Number 1, looking at the periodic table, what is the ground state configuration for chlorine? Meaning, when all of chlorine's electrons are where they're supposed to be, how many electrons fit in each principal energy level? Secondly, I want you to determine 2 or 3 excited states for chlorine. For example, one of chlorine's electrons jumped up to a higher energy level. This is chlorine in the ground state. Chlorine is in the 3rd period of the periodic table, so it will have 3 rings of electrons. And that first ring will only hold 2 electrons, just like we did with Bohr models. There are 2 elements in the 2nd period, so that chlorine can hold 2 electrons in its first electron energy level. It will hold 8 in the 2nd, and then just 7 in the 3rd. Now, if you wanted to do the spdf configuration, these 2 electrons represent 1s2. Here we have 2s2 and 2p6. 2s2 and 2p6. And then for chlorine, we would have 3s2 and then 3p5, depending on what your teacher is asking of you. Now, an excited state would mean that chlorine, one of these electrons, maybe 2 or 3 of them, have gained enough energy to jump to higher energy levels. So the one that I chose is the one that I think is most simple. These 2 electrons are going to stay put, but we have 1 electron from the 2nd energy level jump up to the 3rd. So the excited state configuration would be 2, 7, 8. We would subtract 1 electron from here and then add it over here. These are 2 other answers that you could have. In this case, an electron from the 1st energy level has jumped all the way to the 3rd, or 1 electron jumped to the 2nd and another electron jumped from the 2nd to the 3rd. All of these are hypothetical. We will get certainly more practice with this as we get closer to electron configurations when we study the periodic table. But I think this is a great place to start because it shows not only how electrons are organized, but also how they can move around within an atom. That's all I have for you for today. Please make sure to leave any questions you have in the comments section below the video. Subscribe so you don't miss anything, and I'll see you in the next lesson. Bye!